All right, so hey, this is just going to be a little aside with the Gillespie's algorithm. I was asked to see if it can model the Brusselator. And this one, actually, we can't. We can get it to be kind of Brusselator-esque. Now, the true Brusselator has, let's actually look at it. It has, well, these are two different compounds, X and Y. I also apologize, like my audio has been acting up today. I don't know what's going on, but we'll see if this one works out. It should be good enough to understand. But you see how they fluctuate. They fluctuate in this unique way. But really what's cool is how it kind of finds this equilibrium point. Now I kind of had a hard time modeling this with the SciPy ODE integration method, but you can get it with Gillespie's algorithm. And so it will actually see some spiraling too. So let's get into it. We'll just use what we already had because we already showed that it oscillated. So we're just going to copy. Down here was my attempt to ODE integrate it, and it just kind of clunked out. It's kind of a complicated system, so maybe I'll mess with it more and post later. But okay, so if we go ahead, change this, let's delete two of our plots. We want one plot, or we want one line in our plot. And let's actually just do our X counts against our Y counts. And what this will do is just put the X concentration against our Y concentration. Okay, so we see some sort of thing form. Let's go ahead and increase our T length. And yeah, you can start to see this Brusselator triangle thing start to come in on itself. Let's increase it some more. Nice. Okay, cool. So we're getting a new starting point each time, probably because we're running the reaction randomly, right, each time based on Gillespie's algorithm that we defined in my first Gillespie video. But we get it all kind of, no matter what we start with, it looks almost like the same shape. Now it'd be interesting to see the average of all of these. Now that would be what I tried to do with the ODE integration, but it wasn't responding well to my code today. Yeah, if I clean this up, we can actually label things properly. Let's clean this up. So it's not time, we're doing X counts, concentration, by Y concentration. So if we run it again randomly, you might see something different. Yep, it is a little bit different. Then if we really boost this up, let's actually just really boost it up to 1,000. See if we conk this Google algorithm out at some high number. Yeah, it didn't like that one. Let's set it on one more zero. It's not liking my high numbers. I'm not getting as much line. But anyway, it looks pretty much the same. And so it'd be interesting to find the average when you do this. I hope this helps. Right, what we're doing here is we're just stealing these X and Y's, and so if I just went and swapped out this X count with the Z counts, we would still get some sort of fluctuation. Because right, but based on this system that we defined in my last video, it's this equilibrium. Now you could try and make an equilibrium between two chemicals, and that's kind of what the Brusselator did. They had A, B, D, and maybe even E in their chemical equations, but they really were just interested in X and Y. But of course you could make an easier oscillating system with just X and Y. If you just have to have X go to Y and Y go to X at some rate, maybe you can vary the rates and you'll see the change over time with that, especially with Gillespie's algorithm. It'll be some sort of random thing. And so I hope this helps. I am cheating by using the same code I used in the last video, but it being Friday, I just wanted to get this out to you so that you could work on whatever cool project you're doing for school. Anyway, good luck.